Thank you. It's a pleasure to be here, this time in person. Last year I was here just on the webinar. Much nicer to come here. I will present an update on what we're doing since last year or last year and a half or so, just to give you some idea of the projects which are related to the things Mark was talking about. What is machine learning? It is essentially you try to predict anything that can be predicted. And there's no rules, like in statistics, that it has to be linear, that it has to be certain odds ratio. There's no rules, except there's one very important rule, and that is that when you build a machine learning model, you always have to build with data which is then different than the data you will apply for, because it's very easy to create models where you have a perfect prediction because you overfit the data. That happens also in regular statistics, but in machine learning we are very particularly sensitive to this. And so I will just show you a few projects. Some of them actually will be presented, one of them will be presented tomorrow at AHA. You can look at that oral presentation. Some of them have been presented as CCT, RSNA, and there's some papers. So just a mix of different projects, about 1 or 2 slides for each project, just to give you an idea what we're working on. And so this is a cardiologist here. So this is a very nice article by a cardiologist about machine learning. I found it. I'm a computer scientist and computer engineering kind of person, but I worked with cardiologists so long that I started to think a little bit like a cardiologist. I hope. I think it's very important. But I particularly enjoyed that nice review. And there's a very nice slide here showing a figure, which you can see. You have a patient, and the patient has certain features. So that's one way of looking at this. Could be blood pressure, could be some imaging result, and then you try to predict, for example, heart attack. And yes, okay, heart attack will be corresponding to those kinds of patterns. So one very simple way you could look at that machine learning is that you would put, like, let's say you have just 2 features. And you say, well, these people, like when they have this kind of combination of features, they don't have heart attacks. But these people here, they maybe have heart attacks. So you try to cluster and find what kind of combinations of feature will give you a heart attack. That's a very simplistic way, but actually there is an algorithm which is called K-nearest neighbor, where you try in multi-dimensional space, you look like, what's the, like, in like your physician's mind, it would be like looking for some similar patient to which heart attack happened right after. So that's basically how computer works. So that's one concept that is very interesting. The other interesting concept in machine learning, which we use a lot in all these papers I'll show you, is that we use something called boosted learning. And that is a very powerful feature, which very much works a little bit like you have different versions of the algorithm, or you sort of like try different approach, and you try to find the best solution. But then maybe you change some parameters, you try like a different model, or sometimes even totally different approach, and you get some other answer. So you try to divide who is normal, who is abnormal. But at the end, you maybe have 3 or 4 or 5 or 10 different models. But then imagine if you had like 3 or 4 doctors reading the scan, and each of the doctors will give you a little different approach, and some of them will be false positive and so forth. But when you put them together, it always works out that you get a better result when you have this kind of multiple one. This is called boosting. So that's another thing we use in machine learning. And so this particular paper was actually using boosting technology to show this machine learning prediction. And this was 5 years, not 1 year. I wish we could do 1 year, but this is the problem is that you have less data. I fully agree. 1 year is very powerful. 6 months will be even more powerful. The problem is the amount of events you get. Yeah, but this is very, very, so in this paper, this is a confirmed registry of CT scans when there was over 10,000 scans with suspected coronary disease. And we have various features, and you can't read it very well, I'm sorry, but there's like many features. One of them is age, of course. Age is very important in prediction in this case was prediction of death. And there's many features coming from the CT scan, so there'll be some stenosis and so forth. And so there will be some green features that the clinical feature, and blue will be the imaging features come from the images, and you mix these things together, and you do something called, I mentioned this importance of this separating the test from results. So what we do here, we do something called tenfold cross-validation. We use it in all these methods. We take 90% of the data, we build a model, and then we test it on the remaining set. And then we mix it again, and then we will do another model, different model. We test it on another 10% of data. Then we stack it together. That way we can actually look how model works, always built from separate data, but we actually can evaluate it in a large method. This is a widely used computer machine learning technique. And when you see this, look at the results here. This is the machine learning boosted model. This is the Framingham risk score in predicting that. And those are the variables, segmental involvement scored and some segmental score from the CT scan. So look at the power of this kind of prediction when you can do it. And this is done, this will be, so how would you use it? You would have like a calculator, which you could just have all these variables somehow brought from the electronic health record, and it will give you a probability of death in this case. And this Duke index. So all those are sort of together, but this is a very powerful technique. And it was in 10,000 patients, so with about 1,000 events or so. So one thing, I just won't show you too many statistical slides, but something we wanted to highlight. We always hear this split sample here in cardiology. People use, we'll take half of the data, we build a model, and then use the next half of the data, we test the model. And so that's a traditional thing I see in JACC and all these journals. And that's what you can use for machine learning. But what happens is that we tested this. If we use different people, we just mix different people, and we say, okay, we use some other 50%, different people, and we then test it on the different group. That's the kind of, this is in about 1,000 patients, we get that much variation. So variation is huge. So when you do this tenfold validation, you are sort of in the middle, and it doesn't matter which people you select and so forth. There's like some even more sophisticated method, which is even better. But basically what we're saying is that you should use these techniques, because otherwise it really, your result is kind of random depending on which patient you put into this test and which patient you put into this validation group. So that's an important thing when you do this machine learning models. So the other way we could look at the data is kind of interesting. This is our recent paper in JACC Imaging, just came out, where we look at the 3-year prediction of MACE. So they were shorting it up a little bit, but this is a small sample. But here we can look at it, when we build this model, we can then look at this machine learning score, which will be some kind of probability. And you see here we can have a very high probability of MACE, up to 50%. And this will be the actual observed, how many, in this percentile, like if we find this kind of percentile of people, 95th percentile by machine learning score, we can see what was the actual event rate in this group. And it was actually 50, close to 50%. So this is, we are matching what actually happened. The gray bars are what happened in those percentiles, and the red curve and the red dots will tell you what was the probability predicted by the machine learning. So this is the kind of technique, this is kind of a version of the Breyer score. And this is one way to look at how your model is showing the data. And so how can you use it clinically as a doctor? This is a lot of math and all this. How could you use it? So we think, well, for example, this was the MPI, myocardial perfusion imaging. So what you could do is you get a scan. You typically get your quantitation here, QPS, or whatever, like that we do polar maps. And then there's some various variables which can come from the computer. A lot of variables, like we have TID, we have ejection fraction, volumes, like maybe there's 100 variables which come from images automatically. You don't have to do anything. And then there'll be some data coming from the clinical, from electronic medical records. And then that will give you your risk. It will just give you like a bar, and just like your hurricane prediction or how you're showing, you predict, okay, well that patient is pretty high. And so what's interesting here is when we look at this, this method, is that people in this highest, percentile of machine learning prediction, which as you've seen was matching very much what actually happened, 19% of them were called normal, like clinically normal scan and normal diagnosis. So that's a large number of patients. This is a small study we did, but it can show you the power of sort of sorting out these people who actually are at the high risk from the people who are not. That's pretty much what we are trying to do here. So this study will be shown tomorrow at the AHA sessions. I don't know if you can see it very well, but this data is from Dr. Blaha, and this is a large consortium with 66,000 cases with calcium scan, and there are some existing. So this is a very sort of hard to see here, but it's a very large data set with cardiac death and cardiovascular death. So it's 500 cardiac deaths and 971 cardiovascular death. And here is your ROCs, and here this is just an area under the curve. So you see the red one, the machine learning, with these boosted methods, comes up to 0.85. 0.85 is the prediction of cardiac death. Is very high prediction of 12. This is a very long-term prediction, so we can, well, you know, but again, you can see the one-year prediction is going to be only 50 events. But it is highly statistically significant from variables such as calcium score, or this pooled cohort equation, the green one, which was shown before. They're all performing very well, but machine learning is highly significant, and it will give you a much more accurate answer compared to all these existing methods, and also higher than a calcium score and the methods as used right now. We could also do machine learning on clinical data alone. So take out the calcium score, and that's the red, very red one here is the machine learning with calcium and the clinical data, and the one, the brown one here is a little lower. It will be lower, but just very little. You can predict quite a bit from just clinical data alone. But calcium scan does add, even in this kind of large population with this latest